Last time we had seen some problems. Let's continue with the problems. We were with the problems related with the pH of the buffer solution, which were related to Henderson-Hasselbalch equation. The two types of the buffer we had seen: the buffer of weak acid and it's salt with strong base. This is one buffer, and the second is the buffer of the weak base and it's a salt with a strong acid. Problem number first. Calculate the pH of the buffer solution which is obtained by mixing 50 ml of 0.1 molar NH4OH. Ammonium hydroxide with 50 ml of 0.02 molar this is 0.01 and 50 ml of 0.02 molar ammonium chloride. So this is a basic buffer which is formed by mixing the weak base with its salt of a strong acid. So these two are mixed, and we have given if the ionization constant of ammonium hydroxide, that means the value of Kb we have given. Kb is 1.8 into 10 to the power minus 5. So this is the given data, and we have asked to calculate the pH of the buffer solution. Now to calculate the pH of this basic buffer, the formula is pKb, pH is equal to pKb plus log of concentration of the salt divided by the concentration of the base. This is what we have given. Now here two solutions are mixed. Total solution made is 100 ml. Therefore, we will have to first calculate the concentration of the base when these two solutions are mixed, and also the concentration of the salt when these two solutions are mixed. Therefore, first the concentration of the salt. The concentration of the salt is taken to be 0.02. How many ml of it are taken? 50, and the total volume of the solution. These two are mixed, 50 plus 50. So total solution will be made 100 ml. Therefore, the concentration of the salt when these two are mixed in the mixture, this comes out to be 0.01 molar. Similarly, we can calculate the concentration of base. Concentration of base is 0.01. It's 50 ml are taken and the total solution is 100 ml. Therefore, the concentration is 0.05 molar. So we have got these two terms, that is the concentration of salt and the base. Now we need to know pKb. We know the value of Kb. Therefore, we can calculate pKb as pKb is equal to minus log of Kb. Just substitute the value 1.8 into 10 to the power minus 5. So this comes out to be pKb is 4.74. Now pH is equal to pKb 4.74 plus log of 0.01 divided by 0.05. So this is equal to 4.74. This comes out to be 0.699. This is equal to, therefore, the pH not plus minus 0.699. So the pH is 4.041. Okay. Actually, this is the basic buffer. So this is the formula not of pH, but this is a pOH. The formula for the basic buffer is to calculate pOH is equal to pKb plus log of concentration of salt divided by concentration of the base. So we have got this pH and not pH, because Henderson-Hasselbalch formula for the basic buffer is of pH. Therefore, this is the pH, so we can calculate pH. This is equal to 40. Therefore, pH is equal to 40 minus pH. How much pH we have got? 4.041. So pH of the basic buffer is 9.959. So this is what is the pH of the basic buffer that we have got. Now the next problem. Calculate again the pH of the buffer solution obtained by mixing. Now acidic buffer is formed. 10 gram of acetic acid and 15 gram of sodium acetate. Now directly we have given weight of the acid and the salt taken. 10 gram of acetic acid and 15 gram of sodium acetate is given. These two are taken, making the volume of the solution 1000 ml. So here the solution made is 1000 ml. That means a liter of solution is made. Now we will calculate the pH therefore. Now see, some of the data is given here. The value of pKa of acetic acid given is 4.74. Then the molecular weight of acetic acid given is 60 grams per mole. The molecular weight of sodium acetate is 82 grams per mole. So this is the data we have given. Now we will calculate the pH of the solution. Now this is an acidic buffer, and here we know the formula to calculate the pH of the acidic buffer. pH is equal to pKa plus log of concentration of salt divided by concentration of the acid. Now therefore, first we will have to calculate their concentrations. To calculate the concentration, what we will have to do is the weight of the acid per liter divided by its molecular weight. So 10 gram, this solution is made to 1000 ml. That means in a 1 liter, the acid present is 10 gram divided by its molecular weight. Therefore, the concentration of the acid, this is the concentration of acid, 0.167 mole. Now concentration of the salt. How many grams of salt are taken? 15. Its molecular weight 82. This is per liter, this is also per liter. That means for 1 molar solution we need 82. If 15 grams are present, therefore how much is the molarity? 0.183 mole. So this is the concentration. Now we know the concentration. What we need more is, we have already given pKa. Therefore pH is equal to pKa plus log of concentration of salt divided by the concentration of acid. So substitute the terms. 4.74 plus log of 0.183 divided by 0.167. So 4.74 plus 1.099. So this comes out to be 5.839. So this is what is the pH of the buffer which is formed by mixing these two entities together. Now the next problem. Now this problem is related to hydrolysis constants of salts. We had seen the equations. Calculate the hydrolysis constant and degree of hydrolysis of 0.5 molar sodium acetate. We had seen the salt hydrolysis of the different types of the salt. we have given here the salt of strong base and weak acid. The sodium acetate we have given, which is a salt of weak acid and strong base. And we have given two values. We have given the ionization constant of the acid, weak acid, 1.78 into 10 to the power minus 5, and the value of ionization constant of the water we have given 1.00 into 10 to the power minus 40. And we have asked to calculate KH and H, degree of hydrolysis and hydrolysis constant. So therefore, for the salt of weak acid and strong base, its hydrolysis constant formula is Ka divided by Kw divided by Ka. So let's substitute the values. 1 into 10 to the power minus 40 divided by Ka we have given 1.78 into 10 to the power minus 5. That means hydrolysis constant comes out to be 5.62 into 10 to the power minus 10. Now H, this is equal to, the degree of hydrolysis is equal to square root of hydrolysis constant divided by the concentration. Now here in the problem we have given 0.05 molar of sodium acetate. That is the concentration. So square root of 5.62 into 10 to the power minus 5 divided by C. Concentration is 0.05. Sorry, this is minus 10. 10 to the power minus 10. Its square root will be 10 to the power minus 5. And the square root of 5.62 divided by 0.05 is 10.6. So this is what is the hydrolysis constant, or this we can write as 1.06 into 10 to the power minus 4. This is what is the degree of hydrolysis of this salt. Now the next problem. Calculate the pH of 0.01 molar potassium cyanide. Calculate the pH of 0.01 molar potassium cyanide at 25 degrees Celsius if Ka of HCN, hydrogen cyanide, is 4.9 into 10 to the power minus 10, and the ionization constant for water 1 into 10 to the power minus 40. These two values we have already given, and we have asked to calculate the pH of this salt solution on a hydrolysis. KCl, potassium cyanide, this is a salt of strong base and weak acid again. KCl, HCl is a weak acid. This salt is formed from potassium hydroxide and a hydrogen cyanide. That means a strong base and a weak acid. HCl, that is the acid used here is HCl, hydrogen cyanide, which is a weak acid, and KOH, that is a strong base. So this is the salt which is formed from strong base and weak acid. Here the value of the ionization constant for the weak acid, hydrogen cyanide, is given, and the ionization constant for the water we have given, and we have asked to calculate the pH. The formula to calculate pH is equal to half of pKw plus pKa plus log C. This is what is the formula to calculate the pH of the solution which is formed after the hydrolysis of this type of a salt. Now pKw we will first calculate. pKw is equal to simply minus log of Kw. So minus log of 1 into 10 to the power minus 40. So this is minus log of 1 minus, as this is a multiplication, therefore according to the rule of logarithm there will be addition of the logarithm of the two terms, but this is having negative sign, so minus log of 10 to the power minus 40, which is equal to log of 1 is 0. Now plus minus 40 minus in 1 into minus 40, because this negative sign is already there, into log of 10. So this is plus 40 log of 10 is 1. So pKw is nothing but 14. pKa, we'll first calculate pK, minus log of Ka. Substitute Ka minus log of 4.9 into 10 to the power minus 10, and this comes out to be 9.31. See here it will be minus log of 4.9 plus into bracket minus log of 10 to the power minus 10. This, the log of this term will become 10 minus log of this term, and that is, so answer is 9.31. We need to calculate again log C. Concentration is 0.01. So log of 0.01, it is simply minus 2. So pH is equal to half of, let's substitute the values, pKw, that is 14, plus pKa, how much pK we have got? 9.31, and this minus 2. So this is half into 21.31. So this is 10.655. So the pH of the solution after the hydrolysis of this salt is 10.655. That means the pH is basic. That means on a hydrolysis of the salt of strong base weak acid, the solution which is formed, that is basic in the nature. Rest of the problem, that is the problem depending on more sum of the hydrolysis, constant degree of hydrolysis, and the solubility product we will see in the next lecture.